Our presentation today features the Michigan Department of Transportation's use of externally bonded fiber-reinforced polymer systems for bridge element strengthening. We're pleased to welcome our presenters, Matt Chynoweth, Chief Bridge Engineer and Director of the Bureau of Bridges and Structures with the Michigan DOT, Steve Kahl, Bridge Construction and Modeling Engineer with MDOT, and Jason DeRuyver, Bridge Design Squad Leader, also with MDOT. Matt?
Thank you, Mary Lou. And welcome, everybody. Good afternoon or good morning, depending on where you're at. Jason and Steve and I are very pleased to bring you our presentation. What we're going to talk about today is two projects. We're going to do two case studies where we have used bonded FRP systems for column confinement and passive reinforcement. So we're going to talk about I-75 over the Rouge River, which is the biggest bridge in the state of Michigan. We're going to talk about a very complex ramp within our I-75 M8 interchange. Both of these are in the city of Detroit, and I'll show those in a map in a minute here. We are going to talk about the guide specification for bonded FRP repair update, the AASHTO guide specification. There are currently some limitations to that, which we'll get into in a little bit here, and that is currently, that is actually very quickly going to be under contract to be updated. And then just want to touch briefly on the future of FRP and infrastructure as it relates to inspection of FRP elements, load rating, damage, all of that stuff. So just a brief hint as to what we need to work on as an industry with FRP systems. So on the left is a map of our Lower Peninsula, if you're not familiar with Michigan, and the two bridges in question here are in the Detroit area. The first one is I-75 over the Rouge River, as you could see from the first star there, and then the second one is about 40 miles away, which is within our I-75 M8 interchange. So how are these FRP bonded systems, how is this relevant to ABC? How is it relevant to our movement towards accelerated construction and less user delay? Well, the use of the bonded FRP systems actually resulted on these two projects we're going to talk about today, resulted in no impacts to freeway traffic above and very little impact to the local traffic below, just in terms of staging and equipment access. So you're driving over the freeway, you would never know that we were working on these bridges. The systems can be installed fairly quickly, either via pre-qualified contract or contractor, as the first one will show, or using direct force maintenance staff, which is how we did the second project that we're going to show today. So the strengthening of these elements, or the confining of these elements, is a viable option for asset management, long-term asset management, which can delay replacement, which obviously, if these elements are replaced, that's a huge impact to mobility, huge impact to traffic. And so that's how these systems can be relevant to an ABC type of application. So the first project that we want to talk about, this is our I-75 bridge over the Rouge River. This is a 109 span composite steel structure consisting of many cantilever and continuous spans with a main 3-span continuous unit over the Rouge River. And as you can see, this chart shows the largest bridges that we have in the state relative to deck area. And I think a lot of folks, associate the Mackinac Bridge, which is the second one there, as the largest bridge in the state. It is in fact the longest, but when you consider the length and the width, the total deck area, our Rouge Bridge has 1.1 million square feet of deck area, thus making it the largest in the state. And this is just a cool photo of the bridge in action. So some facts about the bridge. Prior to 2018, the bridge was considered to be in overall poor condition. We had a deck NBI rating of 4. However, the steel girder superstructure and the piers were maintaining them in good to fair condition. So knowing that we were going to have to do something with the bridge deck, we set out on a pretty comprehensive asset management plan, and we looked at all options for rehabilitation. We looked at a deck replacement option, we looked at a bridge replacement option, we looked at different types of bridges that could cross this, we looked at post-tension segmental, and ultimately what we decided was, due to the fact that this particular bridge represents the lowest point in the Rouge River corridor. This river has a lot of maritime traffic serving the Ford Rouge facility, and at 110 feet over the channel, this is the lowest crossing of the entire Rouge River basin, so we knew we would have to raise the bridge. There's interchanges either side of the bridge, either side of the river at each touchdown point of the bridge. And so all of that led to cost estimates in the $400 to $500 million range to replace the bridge. But again, since the steel girder superstructure is in fairly good condition and the piers can be maintained in good condition through various asset management applications, we ultimately decided to replace the bridge deck. And that was about a $100 million project, and I just want to show some cool pictures of what that looked like. Here's a cool picture of crews setting rebar, and you can see the downtown Detroit skyline in the background with the Ambassador Bridge. Good picture. Here's a cool one of a nighttime deck pour. Again, this has nothing to do with the presentation itself. This is just very gratuitous on our part. We like these pictures. So, what we decided to do with the many, the forest of columns and piers that we have out supporting the superstructure, we've had issues. These particular concrete elements contain slag aggregate, which Steve is going to talk about why that's an issue in a minute here. So we went out and we did a very comprehensive sounding and scoping process for all of our piers, and we developed the plan sheet that you see here for a program of using FRP systems for confinement of these columns. And as you can see, this applies to, piers 24 through 97. We didn't work on all of them, but you can see from the table, we worked on a significant number of these piers, some of them approaching, 90 to 100 feet tall. We developed a specification for column wrapping. We worked closely with Jim Gutierrez from Caltrans, who's very knowledgeable in the FRP systems requirements, and our specification actually addresses the seismic requirements. Even though Michigan is a low seismicity state, we did want to make sure that we were following the best specifications that are out there, and we worked with Jim on those. And as you can see, this is a specification that just sets up the minimum properties. It is it's a generic specification. And this specification, along with some of the example calculations that we're going to show, we're going to make these available with this presentation so everybody can have access to this. We put together this was a MathCAD sheet that we put together, and ultimately we decided, so there's two main specifications we could have used here. We could have used the AASHTO guide specification, or we could have used ACI 440 2R-08. And ultimately, we decided to use ACI. Part of the reason is that AASHTO currently, the current guide specification has a fixed FRP strain limit at the concrete FRP interface of 0.005 microstrain. So you really don't get to mobilize more of what strain the materials are capable of. ACI allows FRP strains up to 0.009 microstrain, depending on the concrete compressive strength, and it maxes out at an allowable concrete compressive strength of 8 KSI. The other big difference is that AASHTO specifies a fixed strength reduction factor of 0.085, which is quite restrictive, considering that the entire guide specification really limits the use of these on flexural members, which have relatively ductile types of failures. Whereas ACI follows, the ACI 440 follows the general provisions of ACI 318, which allows different strength reduction factors for a tension-controlled failure, which in this case would be a 0.9 strength reduction factor. And if we had a compression-controlled failure, we could use 0.65. So overall, we thought that the ACI specification offered much more flexibility for us. And as you can see from the sheet here, we do have rectangular columns. So we selected those appropriately and started entering in strain values and the tensile modulus. We go through the inputs for the concrete and the strains in the concrete. And again, we calculate the equivalent circular cross-sectional area for the column. And we calculate the effective confinement ratio per ACI. We go through all of the applicable shape factors, the FRP strain efficiency factors, the strain at failure, and then we can calculate the maximum compressive strain in the confined concrete. And from there, we get the actual additional capacity provided by the FRP system to the benefit of the column. And so what I'm going to do is I'm going to turn it over to Steve, who's going to walk through the particulars of why slag aggregate is an issue for us, and then we will go through some of the construction of the project. Go ahead, Steve.
Great, thanks, Matt. This is Steve Kahl, and one of the reasons why we wanted to use carbon fiber as a passive external reinforcement to bolster the repairs is that the slag aggregate is not good for longevity in terms of crack resistance. It is a highly porous, glassy material, as you can see from the picture there, magnified 15 times, and I drew a little outline around it to pinpoint it or separate it from the surrounding paste, but it's obviously apparent. This material has minimal fracture toughness, and cracks go right through the aggregate, unlike standard aggregates where they bridge cracks, and cracks have to expend energy to work around. They'll just plow right through the slag aggregate, which means you have essentially no crack resistance and no aggregate interlock after the crack formation. So if you do any patch repairs with slag aggregate, you want to first carefully make sure that you define your removal areas, because if you take a hammer and chip away, you'll find you won't be stopping. So you have to essentially carefully lay out the repair area and stay within the confines of that area. And you're also going to need a way to maintain or hold that patch in place throughout the life of the structure. So anyhow, as we can see here, the first step in applying this FRP reinforcement was to remove the unsound concrete from the pier columns and expose the steel for a better bond and performance. And in addition to that, in addition to the FRP, we wanted to ensure longevity by placing sacrificial anodes to protect the steel from the ring anode corrosion effect, which essentially combats the issue when you place new concrete next to old. You form a electropotential that accelerates corrosion in the old concrete. So to mitigate that, we threw in the sacrificial anodes. So you remove the old unsound concrete, and then you begin to prepare the column for the FRP wrap. Are we on to the next stage? Okay, excellent. First off, of course, you apply the patch material, let it cure. You want to make sure the edges on square columns are rounded to reduce the stress on the FRP, and typically that's a 1-inch radius. Certain manufacturers may specify a preferred radius. Some may be smaller or larger, depends on the system, but they're roughly around the 1-inch ballpark. So you patch the material, prepare the surface, and apply the primer, and then you're ready to actually apply the wrap. The subcontractor for this particular project was experienced in FRP work, and the spec required that the contractor choose a specialist that was experienced and also to have that representative on site for troubleshooting and guidance. The FRP subcontractor, since they were experienced, they were able to use a particular device to ensure that the carbon fibers were fully saturated with the epoxy bonding material. They used an impregnating device that, similar to the old laundry squeegee rollers, you pass the fibers through a saturated roller system that makes sure the individual fibers are coated with the epoxy, and then they simply carefully place the wraps around the columns and then roll them into place to get rid of air bubbles. And so after the FRP is installed, typically you put another layer on the top of the FRP of the epoxy to further coat and make sure that the fibers are coated and bonded with the epoxy system. And then after that curing takes place, you top coat it for environmental protection and against UV protection, although the epoxy itself also has chemicals to resist UV degradation. The top coat is generally gray concrete color, and depending on the particular manufacturer, they'll have specific requirements. They'll have either their own brand, or they'll have a list of compatible products you can use for top coat for both aesthetics and for environmental protection. As a summary, I guess, of the project, it was fairly large, but compared to replacement, not really. This project was about $6.5 million for everything, including 23 rehabilitated pier vents, or a total of 71 columns. Quite a bit of patching concrete was used for almost 500 cubic yards. 49,000 square feet of the FRP reinforcement was applied. And this was all done in one construction season. Since, again, we were below traffic, we didn't have to worry about traffic shifts or any other restrictions in regards to that. The contractor was originally Posen Construction, now called Z Contractors, and the specialist was called Structural Group. And they did quite well. The quantities estimated and the quantities that were actually paid for were fairly close, which again, when you work with slag, you have to remember to limit the repair area so you don't wander too far, because that would eventually lead to quite significant increase in your quantities for patching. So overall, the project was well within what we thought it would cost. And initially, we estimated $25 a square foot for the FRP cost, and the low bid came in at $27. So we were quite happy with that.
Thank you, Steve. I'm going to go back up to one photo here. I did see a question ahead of time about these deck drains. What did we do? These deck drains were simply cut to allow us to do the FRP repairs, and then they were extended down to a splash block, as part of the final, pieces of construction here. So I don't want anybody to think that we just cut the downspouts and let the water free fall 90 feet. We did not do that. Okay, so that represented an example of a project that MDOT did. We designed in-house and let as a capital project. I'd like to show a different example now. This is a project where we worked with a local university to develop a repair scheme, and then our region bridge support folks and direct force maintenance folks did the repairs. And so this is in a very busy interchange on Detroit's north side. The previous project was on Detroit's south side. So this is our I-75 M8 interchange. This is a full freeway-to-freeway interchange with a lot of complex movements. And what we have on this ramp here is this is a ramp that takes you from one of the service drives to northbound or southbound I-75. And it's got a very unique configuration. It is you can see from the geometry there with the service drive coming underneath, we don't have a cap and column type of a situation. We have a single column with a very massive knuckle bearing and then intermediate bent. And this is a fixed bent, so it's allowing for rotation but no translation whatsoever. It's on a curve, 950 foot. And non-uniform span length, so we don't have balanced span conditions either side. We have an 86-foot span on one side and 137.5-foot span on the other. And so all of these conditions and this structural configuration led to some forces on this column that caused cracking and spalling. Just some details here as to, this was built in 1967, by the way. And again, just some details here as to the location of the column in profile view. And here is what it looks like in plan view. And you can see it's a very short span coming into it, and then a longer span going towards the freeway. And at this time, I'm gonna turn it over to Jason DeRuyver, who's gonna describe some of the cracking and spalling that we found, and then the repair procedure that we developed.
Thanks, Matt. As you can see here, the forces Matt was describing caused several cracks and spalls near the top of the column. And we just have a few slides here showing different views of those cracks and spalls. It's basically on all four sides of the column near the top. All right, in order to do the design, we reached out to one of our universities. In August of 2013, we reached out to one of our universities, Lawrence Technological University, as an expert in carbon fiber design. And he analyzed the bridge and all the loads, and he came up with the actual design for us and sent us over this MathCAD sheet. Let's see about that.
Yeah, as you can see here, we're going to go through this. We will make this MathCAD available on the FIU website here, but this just goes through all of the traditional calculations, the material properties calculations. Went through an analysis of the load carrying capacity of the pier on its own, and so unstrengthened and strengthened. We go through, again, this uses just like we did before, this uses the ACI methodology. So we're calculating the strains based on ACI, checking the confinement, checking, calculating our moduli, and then going through and actually calculating what percentage of additional axial capacity this passive system will provide for us. And from all this, we calculated the confinement was okay. It kept strains within the allowable. And again, this is a passive system. This is not an active system. And so the total contribution with the new system, we increased the capacity by 42%. And Jason's going to talk through the actual repair of the column.
All right, so before we could install the FRP, a few steps had to happen first. We had to close that local road service drive underneath the bridge in order to install all of the temp supports that we need to install to unload the column. And then we had to patch the concrete. Hit the fast forward button here. You can see that the concrete is patched. And what I'd like you to notice here is that the edges of the concrete patches are pretty rough and irregular. And also that we didn't use any special patching concrete. We just used the standard 4,500 PSI mix that MDOT specs out. Here we are preparing the column surface with a grinding wheel. And also, after we ground all the edges of the patches and all the surface irregularities, we then needed to go in and grind the corners. The fabric we were using required only a 3/4 of an inch minimum radius. In order to finish the concrete surface preparation, the surface needs to first be sandblasted to a minimum ICRI surface profile of CSP3. Basically, that is just removing all dust, dirt, bond-inhibiting compounds such as oils. And then after preparing the substrate with a light sandblast, we just went in, and what we see here in the picture is we're applying the first epoxy that gets applied, and this is the primer. The CSP3 shot blast also opens up the pores of the concrete to allow the epoxy to soak into the surface better,
but we don't want to be more aggressive than that with our surface preparation, because then we start getting into introducing more surface irregularities. So again, we did the CSP3 to just clean it and not have a lot of surface irregularities, so that we don't use as much of what we are seeing here in the next step, which is the epoxy leveling putty. This basically fills in all the little tiny surface imperfections, voids, bug holes, to get a better adherence to the concrete. This is applied immediately after applying the primer. There's no cure time to wait in between. Immediately after applying the epoxy, we're applying a layer of the saturant. The saturant gets applied just basically using standard paint rollers that you would use. And then every manufacturer, based on the thickness of the fabric you're using, will give a recommended coverage rate. For the fabric we were using, we estimated a rate of 45 square feet of coverage per gallon of epoxy. So once the first coat of saturant is applied, we applied the fabric to the saturated surface. While the saturant was still wet, any ends that we had needed to be lapped 4 to 6 inches, depending on what the design requirements and the fabric thickness and the manufacturer recommended. After the fabric is hung, we used a rib roller, rolled across the surface of the fabric in the direction of the fiber, helping to remove the air bubbles. The rib roller also presses in the fibers to help ensure they are fully encapsulated in the epoxy. The fiber should be rolled until the saturant starts to bleed through the fabric. After the fabric is set in the saturant, it is then coated with an additional layer of saturant to finish encapsulating the fibers. Lastly, since this was adjacent to traffic, we decided to coat the entire column with a colored concrete surface coating. And as you can see in the picture, that you can barely see where the repair area was. Project summary: the carbon fiber design was completed in August of 2013, and the design and construction of the detour and temporary beam end supports was completed in August of 2014. The concrete was patched by state forces in August of 2014, and then the FRP was installed 28 days after the concrete cured, or after the concrete cured for 28 days. And the FRP only took us 1 day to install, and the cost of the carbon fiber materials was only $2,470. Lessons learned. It's quite complex engineering, as you saw earlier, but it is really a simplistic installation. Our state maintenance crews, and I'm guessing your state maintenance crews also, are very capable of doing a repair like this. And the one unique thing I needed to throw in here is I had to sign an end-use agreement when I bought the carbon fiber to promise I wasn't going to use it in the manufacturing of weapons of mass destruction. Here's a view of the column, and today, at its most recent inspection in 2019, still looking in very good condition, and you still really can't see the repair area.
Excellent. Thank you, Jason. So just 2 quick things here to wrap up. As I mentioned earlier, so these 2 examples both use the ACI methodology, and we do have an AASHTO guide specification for the design of bonded FRP systems for repair. It was first released in 2012, and it's not being used, it's not being used as much as I think it should. I think this should be a go-to, especially for a lot of us that are AASHTO states. So the T6 committee for the Committee on Bridges and Structures, that's the FRP Composites Committee. I am the chair of that, and we developed a research needs statement, and it was selected by NCHRP. It's going to be an NCHRP 20-07 task 428, and we are going to update this. We're going to put together a second edition. And we're basically going to try to unify the AASHTO and ACI provisions. We want to also ensure engagement with industry so that there's alignment with what industry can manufacture and develop for us. We also want to update it to include near surface mounted strengthening applications. This is another one of those very popular things that's done out in California, and Jim Gutierrez does a lot of work with that. And we obviously want to make sure that the AASHTO specification is using the appropriate strain compatibility requirements, and we're not limiting the strains on the material to something too artificially low. So the schedule on that, there was a researcher selected just about a month ago. We feel it'll probably be a 1-year effort, maybe less, with a goal of spending, 2019 updating this, finalizing this, running it through the committee, and then taking it to ballot at the 2020 AASHTO Annual Committee on Bridges and Structures meeting. So to close, I just want to have this group think about, as we're using these things, as we're using not just the bonded system repairs, but we're using, glass fiber rebar, carbon fiber rebar, we're using composites more and more. How do we deal with this from an owner perspective, from an inspection perspective? We recently, as part of the EDC5 initiative, we had applied for more deployment of FRP in our infrastructure as an EDC5 initiative. And when it wasn't selected, I engaged with FHWA on, okay, what are the challenges to this being fully, implemented and fully on board? Why was it not selected as an EDC5 initiative? And they asked some very good questions, of which our T6 committee did not have the answers, such as, what is the life cycle maintenance? How do bridge owners notify their inspectors that this is an element that contains FRP? What is the performance if damaged? How do you load rate these? How do you load rate them for overloads or permit loads? If you have, let's say you do an FRP repair of a pre-stressed I-beam, how does that go into the superstructure load rating calculation? And then just an overall better understanding of failure modes. Through a lot of the research we've done with Lawrence Technological University, we know that a question that's always come up is, how is it resistant to fire? And what we found is that it actually performs very well when damaged by fire and under fire. What we find happening is that the epoxy, depending on the temperature, the epoxy initially will burn away, but the fibers still stay in their stressed state and still would act to confine or reinforce. And that's based on a lot of testing that has been done. So what we've challenged ourselves as an AASHTO T6 committee, and we're also working with the TRB AFF80 committee on composites, is, how do we consider future research geared towards a better understanding of how these elements will function? How long do they last? And AASHTO T6 and TRB AFF80 also been engaging with industry, because again, we need to be able to specify something that industry produces. So this is really taking on the direction that FHWA is going in terms of a risk-based approach to the design, construction, and the network management of structures that have FRP systems. And with that, I will turn it over. That completes our formal presentation, and I will turn it over to Paul for questions.
All right. Thank you, Matt. And at this point, we'll send it to Paul. Paul, it's all yours.
Thank you, Ettore. All right. We've got a lot of questions, everyone. It's about 12:45, so we'll have a few minutes to go through them. We've got a whole lot that came in beforehand, and we've got a good many that have come in during the session itself. So with that, we'll go ahead and get into them. I've got them broken down to design, in construction, and maintenance, and cost. So we'll go ahead and get to it. There's a couple of preliminary questions that had come out, and Matt, you commented on this, but I just want you to say it again because everybody's very interested. Is will there be handout materials from the presentation? Is it possible to get a copy of the materials and references? So go ahead and say that again for us.
Yeah, so we will send to Mary Lou and to Torad. We'll send the specification. We just gave you a screenshot there, but it's a 6 or 7 page specification. We'll send you our specification along with the 2 MathCAD sheets. The first one that we used on Rouge River for the confinement, and then the second one that we used on I-75 and M8 for the confinement and increased axial capacity. So we will have those resources for the website.
All right, that'll be fine. Are they also on your Michigan DOT website at all, or at least the special provision?
The special provision was out on our previously approved website at one time, and then we actually upgraded our standard specifications, so I don't believe it's out there right now. So that's why we'll make it available as part of this.
Okay, that's fine. The only problem, people may be interested down the line, if you make changes to the special provision, I don't know that we'll pick that up on the website. So anyway, that's on the ABC website. So that's people had asked about whether it would be available at the Michigan DOT website. That's fine. Let's go into the design questions. And a number of questions came in, and it regarded what service life you expect to get out of the FRP.
Go ahead, Steve.
30 to 40 years. We've done a research project through Wayne State University that actually studied environmental factors in Michigan, and they align very closely with what ACI had originally proposed. So we're very comfortable here estimating at least 30 to 40 years if properly applied and top coated, similar to our 3-coat bridge painting systems. So yes, they're going to last a long time.
Okay, that's fine. The question came in regarding fire protection. You had mentioned on that. Can you elaborate on that at all?
Yeah, so we did quite a bit of research with Lawrence Technological University. They have a very advanced fire chamber where they can actually do all of the, it's called an ASTM E101 test, I believe, that you have to be able to withstand a certain temperature. I believe it's 800 to 1,000 degrees for up to 59 to 60 minutes. And what that allows for is if you have a building fire, it allows for the building to be emptied before you get a catastrophic collapse. So we've had elements that we have put in this fire chamber, and as I mentioned earlier, what we noticed is at a certain temperature, the epoxy will combust and will burn away, but the fibers themselves are largely untouched. And so just like with any other element, whether it's concrete or steel, for these 2 particular applications, let's say we had a fire underneath the Rouge River Bridge or under I-75 M8 interchange, we would obviously be concerned about the entire structural system, but we do not need to take into account any special precautions or any special considerations because of the presence of FRP.
Okay. There was a question about any concerns about vandalism.
Yeah, that's always an issue. I think you saw from the I-75 and M8 photos that that does happen. That's where that last coat, that concrete surface sealing coat, is so critical, because that is actually it sometimes is a elastomeric or an epoxy coating that you put on the top that once that cures, that's as good as structural steel coating or anything like that. So yeah, vandalism is something we got to worry about with spray paint, or somebody wants to take a knife to this stuff and try to cut it off. I guess that's always an issue, but it'd be difficult to get through.
Okay. You mentioned the UV resistance. Can you comment on that? Long-term performance?
Yeah, so I mean, obviously these types of repairs aren't exposed directly to sunlight. They're typically under the bridge. But as Steve mentioned, the epoxy that we actually use, or the resin that we use to prepregnate or impregnate the fibers, that contains UV inhibitors, and then the finished concrete surface coating that we apply over the FRP system, that also has a UV protection system in it. So it is an issue for FRP materials. They do degrade due to ultraviolet light, but by coating them, we're effectively protecting them.
Okay. Did you have concerns about the permeability of the concrete and freeze-thaw cycles of moisture within the concrete members under the ramps?
Want to address that one, Steve?
Yeah. Typically, if you're going to do flexural repair on a beam, you'll space out the FRP wraps to a 1-inch gap or so to allow for moisture exfiltration. But as for column confinement, what you're also doing is effectively creating a moisture barrier as well. So long-term studies have shown that that's not an issue.
Okay. Let's go over to the codes. There are a couple of comments on the codes. You mentioned that y'all use the ACI code rather than the AASHTO. Then y'all, I guess, were the approving authority. And the question came in about what were the codes. You've answered that. Where are they approved? Y'all had to make a selection, I guess, is what you did. The AASHTO code wasn't available in 2010 when you did the Rouge River, was it?
Yeah, not that guide specification, Paul, no. What we found subsequently for the next project was that if we used AASHTO, because of the limiting of the strains and the limiting of the strength reduction factor, we found that the number of plies we had to put out there was a very large number. It wouldn't have been, the project wouldn't have been as easy had we used AASHTO. We would have used almost double the number of plies.
Okay. A person had said they were concerned about mixing the two codes. You basically stuck with one of them or the other, didn't you?
That's correct.
Okay. Does this also work for earthquake design, including columns?
So our specification, in working with Jim Gutierrez from Caltrans, our specification does require that the materials meet the seismic requirements that Caltrans uses. But I also know that there are concerns outside of these actual bonded systems. There are concerns with FRP meshes and FRP bars that they are much too rigid and actually brittle in a seismic event. So that's all I know on that. We're not seismic experts here in Michigan. That's maybe one of the few good things about living in Michigan is we don't have to design for seismic. That's probably a better question for Caltrans folks.
Okay. Have you used FRP strips instead of wraps for structural strengthening?
No, we haven't. You're talking about the near surface mounted strips where you actually gouge in a channel and then place the FRP bars and then epoxy coat over them. We have not done that.
Okay. Let's talk for a second about the galvanic nodes. Is it common practice to use galvanic nodes in FRP repair, or was this determined from past poor performance without galvanic nodes?
Galvanic anodes are typically used for patch repair in general, whether or not we use FRP wraps. We found that you extend the patch service life up to 10 years and beyond by using these anodes at the interface, as I explained previously, to prevent the what they call the ring anode corrosion, where by placing new concrete, you're accelerating corrosion potential of the older concrete. So the anodes help mitigate that. So that's independent of the fact that we use them in the FRP repair.
Okay.
Yeah, Paul, we've used those. We've used anodes all over the state where we've just done chipping, and then we wire up an anode, and then we apply a latex patch, and then we're done. So we've done it where we've patched, we've done it where we've patched and applied an FRP system.
Okay. You answered the question about the downspouts. I guess that was on slide 20. The people had picked up on that, I think, from the photos that you submitted in the inviting everyone to come to the to listen to the talk. So people are really looking at those things. In your opinion, what are some of the factors to look for for a good FRP repair project?
So as we kind of touched on earlier, I mean, if you are looking for an asset management strategy to extend the service life of a member, and quite frankly, it doesn't have to be concrete. There's, I believe, a specification somewhere out there for FRP strengthening of steel members. It's a good tool in the toolbox for bridge owners to be able to apply it, strategically to extend bridge service life. We find, especially on our I-75 over Rouge River Bridge, because we have so many columns, because we've made a strategic investment in replacing the bridge deck at $100 million, we want to make sure that those columns last the service life of that new bridge deck. And so using it on the Rouge Bridge is something that we'll do well into the future with a pretty aggressive program. But we've done it on pre-stressed box beams. We've done it on pre-stressed I-beams. I think it's just a good tool in the toolbox for owners.
Okay. Let's go to the construction questions, and we've got a bunch of these. First of all, please address the surface preparation requirements. You mentioned, reconcreting and then rounding the corners. We did get a question that came in during the talk on rounding the corners. Can you comment on that again? And then any other surface requirements? Did it have to be dry when you put it on? Stuff like that.
Well, we'll start with the rounding the corner one with Steve, and then I'll have Jason chime in on the time between coats. So go ahead, Steve.
Yes, this is in reference to the ACI code. Using FRP wraps on square columns is less efficient, and you'll get less strength enhancement using them than you would on circular columns. And in the actual guide specification, they even show a diagram, which is also included in our calculation sheet, which essentially shows the effective confinement area. And it's difficult to describe, more like a pinwheel, I guess, where you have the center of the column faces really not getting too much in terms of additional reinforcement capacity, but it's the corners that a lot of the stresses are distributed to. So you want those corners that are showing a larger compressive stress, that you want the FRP to be smooth. You don't want any kinks in it, to maintain the FRP within its allowable stress range.
Very good. And like we showed in the photos there, we had to do that on both projects. We had to round the corners. So Jason will talk about the times between saturant coatings.
Yeah, you definitely want concrete surface dry when you start, but then when you're applying each layer of the 3 different epoxies, the primer, the leveling putty, and the saturant, you want those still wet. You don't want those set up.
And Paul, another thing to add on that is I'm sure that, there are a lot of, these are FRP systems, right? So it's the FRP and the resin system together. There's a bunch of different manufacturers of them out there, and each one probably has its own nuances in terms of the different coating times between resins and stuff like that. Okay.
That was a comment that came on the bonding agents and adhesives. So that's part of your resin to the substrate, basically. That's all the system is what you're telling me.
Correct.
Okay. Let's go. We got a bunch of questions that came in during the session about the slides. And let's try and ask some of those. How long do you keep the FRP wraps around the concrete columns until you consider it cured? How long does it take to cure it?
Generally, the manufacturers recommend a 24-hour period, but again, each manufacturer will have their own specific set of instructions that you'd follow.
Okay.
But it's generally 24 hours. Sorry.
Okay. Did you remove the rust from the exposed rebars before patching the piers?
Yes, that's a common practice. Whenever you do patch repairs, you clean the existing steel.
Yeah, that's in our specifications, Paul. Whenever we expose steel, we'll do a light shot blast prior to patching.
All right. Were there any restrictions on the concrete removal versus the gross net area of the concrete columns, or the number of vertical bars you could expose at one time?
So that's another thing that's pretty much it's in our standard specifications that when we do these substructure repairs, we like to get 3/4 of an inch to 1 inch behind the rebar because that's the maximum size aggregate of our patching mixture. Because these are multi-column piers, we worked on a few piers at a time, and there really wasn't a restriction on, chipping more than one or height restrictions or anything like that. Like Steve mentioned, with the slag aggregate, you have to be careful because you could literally chip to no good concrete, and so we did set limits on go 1 inch behind the bar for the Rouge Bridge. Jason, do you want to mention something on?
And on the M8 I-75 column that we wrapped, that had been completely unloaded, so there was no concern there.
Okay. Why did the heights of the wraps vary from column to column?
So yeah, that again was based on, we went out in the field and did a pretty thorough sounding of all of the piers, and we really applied the FRP systems to the areas of deterioration. So we didn't just go from the ground level to the cap. We went to the deteriorated areas and went a certain percentage above and below those. And so that's why the heights kind of varied all over the place.
Okay. You mentioned the concrete strength on the patch, I think, on the M8 bridge. What was the type of concrete you used on the Rouge River?
This is our standard latex mixture, which has a compressive strength anywhere from 3,500 to 4,500 PSI. Actually, probably in the higher range of that, probably closer to the 4,500.
Okay. How do you address below grade concrete to the foundation if you have to wrap it?
That really didn't apply to these two examples, but below grade, because again, we were looking at areas that were visibly deteriorated. I suppose if an owner wanted to chase a crack in a column down to the footing, you'd have to excavate down to that interface there and repair appropriately. But we were focusing on purely what was visible deterioration.
Okay. It seems you maintained the flares in the column faces. Did that affect your FRP placement at all?
I'm sorry, can you repeat that? Maintained the what?
The flares in the columns. It looked like maybe some of them were tapered.
That was considered in the design calculations that Lawrence Tech did for us at the I-75 M8 interchange column.
Yeah, that was just that one column, Paul. All the columns on Rouge are square columns, and they're same dimension top to bottom.
Okay, that's fine. On M8, you mentioned removing load from the columns. How was that done?
As Jason mentioned, we had about a week before the repair, we went out and installed temporary supports. So there were temp supports that were actually taking the structure dead load and then live load, so we could do the repair free of loading.
And that's why we had to close the road, because you could see in the pictures that the steel bent actually cantilevered out over the road. So we would install steel columns underneath every beam end, unload it.
Was there any concern about vibration due to freeway traffic anytime?
That's accounted for in our temp support design.
Okay.
Yeah, and in terms of the FRP system installation, Paul, no, that wasn't a consideration for Rouge River.
Yep. All right, that's fine. Please comment on the availability of trained contractors.
There's at this point, there's quite a few out there. It was a little more difficult back in '08, but now it's maturing to the point where you have several national firms that are available to assist you. Structural Group,
Okay.
for example, has offices in many states.
And I just want to comment that we didn't have a manufacturer's representative on site when our state forces did it, but prior to our state forces doing it, a manufacturer's representative did come out and give us a little bit of a training session.
Okay. Did you perform any chloride tests on the columns, or was there a threshold on chloride content you were concerned on?
No, we did not perform that test. Another reason for using the anodes was to counteract any potential issues. And again, since this is substructure, the only potential exposure for chloride would be over the joints. But again, the anodes would help mitigate that.
Okay. Let's look at maintenance. There's a bunch of questions here. Do you have any past experience on strengthening concrete members with experienced cracking under service load? Have you done it before? Was these your first ones?
We've done some before. The traditional way that we've done it here at MDOT is chip and put a latex patch in. But yes, we did have some pre-stressed box beams that we had some shear cracking, and so we applied the FRP systems for additional shear capacity of those webs. And we've done it on some pre-stressed I-beams as well for both shear and flexural capacity.
Okay. You haven't seen any debonding failure in any of these applications, have you?
Not as of yet. We actually have we did some column confinement on a bridge actually just outside of our office here a number of years ago, and the bridge was removed, but we kept the columns. So it's kind of a funny thing. You drive down the road and you'll see a bridge with a set of columns behind a pier, and those are one of our first FRP bonded system installation projects that we ever did. And the bridge is long gone, but the columns are still there, and we still monitor those columns for any type of debonding of the FRP system or anything like that. So it's a good indicator for us.
Okay. There were some questions about FRP inspection methods and the ability to inspect existing concrete elements. Do you want to comment on that at all when they're wrapped with FRP?
So yeah, we've been pretty active in not just these wraps, but we have a couple of the carbon fiber concrete filled tube structures in Michigan. We have some carbon fiber pre-stressed beams in Michigan. And so we make it a point when we do the post-construction inspection, we have actually agency-specific elements that we have on our NDI report that note where FRP members are. So the inspector, if there's anything special that they have to take a look at, they will. When it comes to these systems, basically, we treat it like it's just regular concrete. They'll sound it. If the concrete below the FRP system is debonded, then it'll sound hollow, and if not, you'll get a nice ping. But yeah, we're definitely active in identifying these elements for our inspectors so they know what to look for.
That question came up about there's nothing special about monitoring it other than in the biannual bridge inspection. Is that right?
That's correct.
Okay. And but you do identify the elements, so your bridge inspector will know that you have the FRP out there. That's what you're saying. Okay.
That's correct.
And as far as you know right now, I mean, with what you've heard and everything, it's performing very well at this time.
Yes, it is. Some of our oldest applications have been out there we're approaching 20 years.
Okay.
And they're performing just fine.
Okay. Let's look at cost for a few minutes. There were a couple questions there, and then we're going to have to go. You had the cost of $24.70 for the M8 bridge, and was that the material cost? Is that square foot or?
That was the cost of the carbon fiber and all of the epoxy materials used to install it.
All right, the people that asked,
no concrete cost or labor.
People had asked if that was a square foot cost or a square yard. That's just your total cost of the material, is that right?
That's our total cost of material.
And then you installed it with state forces, so okay. Okay. And then $6.5 million was your Rouge River thing. You've got the cost pretty well covered, so that's fine. That's most of the questions that we've had that came in up until we started asking the questions. I'm going to ask Ahmed if there's any questions we want to pick up before we go ahead and end it. Ahmed?
Yeah, Paul, we do have a few questions left. One question you probably already indirectly answered about corrosion. So the question is corrosion of the rebar in the FRP encased concrete still a concern? How do you know if you have an issue when you can't see the issues associated with corroding rebar?
So the one thing the FRP wrap does is provide a moisture barrier, so you're already bending the curve on the corrosion rate to begin with. And again, we use the anodes to mitigate even further. So these do not have an infinite service life, but again, it's at least 30 to 40 years we're estimating now. So essentially that means that the corrosion of the re-steel underneath the wrap is arrested and dealt with at the time of the repair, and no concerns moving forward.
Okay, another question about unloading. So you mentioned that the column was unloaded prior to patching. When is this necessary?
So the column was unloaded on the I-75 M8 job, and again, that was we wanted the FRP system itself to act as confinement and for increasing the structural capacity of that column. And so anytime that you don't want to lock in any live load strains, I think locking in dead load strains is probably okay, but locking in live load strains, when that becomes an issue, you're talking about restricting traffic. For the Rouge project, it was simply a function of chipping out bad concrete, applying a patch, and then applying the FRP system to confine everything together. There wasn't a calculation there done for additional structural capacity, axial or flexural capacity of that column.
Okay,
so we did not.
Okay, follow up to this question. How did you unload when you did have to do that? Did you have a slide showing how that was unloaded?
No, but as Jason mentioned, so at that knuckle bearing, there's a steel bent, that transverse bent or transverse floor beam that everything frames into. And what we did was we took H sections with steel plates, and we supported each one of those all the way down to the ground in order to unload that particular pier. So we used some steel temporary supports from below under each beam to support it at that intermediate location, so no load was going into the pier.
Thanks, Matt. Jared, I think we're running out of time, so I'll just stop right here.
All right, thank you. Thank you. Excellent presentation. Thanks to all our speakers, and also excellent question and answer period. Thanks to Paul and Ahmed. So we hope that on that note, we are going to end our webinar, and we hope to have you back with us for our next monthly webinar, which will be on Thursday, July 18th, on Missouri DOT's 2018 Poplar Street Bridge lateral slide. And we will have Dennis Hickman, the state bridge engineer, with Missouri DOT with us for next month. So we hope to have you with us again next month, and so long.